This conference will now be recorded.
So, very good evening, students. Today we'll be learning another important topic of this waves chapter, that is superposition of waves, reflection of waves, and standing or stationary waves and normal modes. So these are very important topics of this chapter. So what is superposition of waves? See, suppose you have a string. As you see in this figure, there are 4 figures here. So if you have a string and somehow you create a disturbance like this, so this particular element of the string will be oscillating in the upward direction, right? So suppose it is moving in this direction. If somehow another disturbance is produced on the other side of the string, which is traveling in the opposite direction, so what will happen to the displacement of the element of the string when both of them will overlap each other? So what will be the case in that situation? So this is one situation. Another situation is, suppose you have a string and you have produced one disturbance at this particular element of the string, and another disturbance you have created or produced in the other end of the string, and both are approaching each other. So what will happen? Because these are actually propagating a wave. Propagating wave. Propagating wave. That means the wave after production will travel through the medium. So both are propagating waves. So in both cases, what will happen when these two waves are overlapping? One overlaps like this, and the other one, in this case, suppose overlap will be this. Both of them will overlap at the same place. So what will be the displacement of this element of the string? So this can be obtained from the principle of superposition of waves. That means at any medium, if you have suppose I have some medium and there are number of waves traveling in the same direction with same amplitude. So number of waves with same amplitudes, same angular frequency, and propagating in the same direction in the medium, and somehow they meet or they just passes through simultaneously. That means exactly at the same time, this particular particle of the medium, all of them passes through this particular particle of the medium at the same time. Then what will be the displacement? See, each of them will produce some displacement to this particle, right, of the medium. Particle of the medium, each of them will produce some displacement. Okay, some displacement each of them will produce. But what is the resultant displacement? What is the resultant displacement due to all the waves? So this is actually obtained from the principle of superposition. Okay, so let us now learn the statement. What is the principle of superposition of waves? So The principle of superposition of waves, I'll write it here. The principle of excuse me, position of waves states that when a number of waves when a number of waves number of waves travel through a medium through a medium simultaneously, that means exactly at the same time, simultaneously, the resultant displacement the resultant displacement of any particle of the medium at a given instant of time, at a given instant of time is equal to the sum algebraic sum of the displacements due to the individual waves. Okay, so mathematically what we can write, we'll go to the next page. So mathematically we can write if y1 y2 y3 and like that it goes up to yn. Suppose there are n number of waves traveling through a medium and simultaneously, then the actually these are, suppose these are the displacement displacement produced by individual waves then according to the principle of superposition, position of waves, the resultant displacement of a particle in the medium will be y x of t, suppose, is equal to y1 xt plus y2 x of t, both are function of time and position. Okay, so this goes up to yn. So these are the displacement produced by individual waves for the particle in the medium. Okay, so at any instant of time t, the resultant displacement of the particle will be obtained by summing algebraically all these displacements produced by each individual wave. Okay, suppose if the waves are traveling in the positive x direction, if all the waves are traveling in the positive x direction, then we can write yxt, that resultant displacement will be function of x minus vt plus f of f2 of x minus vt, like that. It could be, so it is the way of representation of the wave when, so this actually, sorry, this can be better understood if we write in the other way, vt minus x or vt plus x. Okay, that would give you the direction whether it is positive or negative x direction. When this is negative minus x, then it is in the positive x direction, vt minus x. Okay, so all of them are having the same speed, and then all are moving in the same direction, that is the positive x direction. And if we write in a short notation, you might have learned this. If not, then learn from here. So this is called summation. Writing all this like many times will be boring or time consuming. So there is a short notation which is called summation. This is actually a sigma sign. So this I goes to 1 to n. That means we are going to add n times. This is actually fn. So we'll write over here fi. So here this indices, this is called subscript. So these subscripts will change 1 2 3 like that, what you got here. So first I'll take I is equal to 1, so f1 vt minus x. When I take x is equal to I is equal to 2, then I will get the second term like that. We can go up to nth term. So I 1 to n. This is called summation. Summation. So summation. This is actually sigma or summation sign, and here the limit has to be given 1 to n. That means you are going from, like, you are adding some nth term starting from 1. If it starts from 2, then n minus 1 terms you are adding. Okay, like that. So from so you have to do like this to get nth term. Okay, so this is actually the statement and mathematical expression for the principle of superposition of waves. I'll state or read out once again. The principle of superposition of waves states that when a number of waves travel through a medium simultaneously, the resultant displacement of any particle of medium at a given instant of time is equal to the algebraic sum of the displacement due to the individual waves. Okay, look here in this figure. So there are two waves over here, you can see that, and each of them has actually the displacement amplitude same. Suppose this is having a minus a amplitude, this has plus a amplitude, because both are in the opposite vibrating in the opposite direction. And see, both of them has the same amplitude. Suppose they have both same speed v, and only one thing is that they are moving in the opposite direction. Now look, both of them are progressing towards each other, as you see in the b figure. So they are coming closer to each other, and at this particular position, they actually overlap. So in this case, you know, this is exactly in opposite phase of this disturbance or wave. Okay, so when the waves actually overlap in opposite phase, the resultant displacement will be zero. We'll show you very soon. The resultant displacement will be zero. Okay, resultant displacement will be zero. So that's why you look, there is no depression at this place. You can look it that there is no gap. This is a solid line. That means what? The string is not at all vibrating at this particular position, because I'm sorry, just a minute. Okay, so you can see here, you can see, if I say this displacement to be, both displacement are actually same in magnitude because the amplitudes are same. So here this will be, suppose, y, and
Ram, no sound, Ram. Hello, Ram. Hello, Ram, no sound, Ram. Ram.
Hello, hello.
Yeah, now only I'm hearing a sound, Ram.
Is it audible, madam?
Yeah, now only it's audible.
So how long?
Yeah, and I nearly
How
6
long you
minutes or
present?
6 to 7 minutes.
My, my God. Okay, then I'll try to repeat. I don't know exactly how much will be repeated. Okay. I don't know how much I have to repeat, but I'll repeat anyway. Hello. So I hope it is audible, madam, right?
Now it is audible.
Okay, I'll repeat.
Okay.
So we have been discussing the principle of superposition. So what is the statement? The statement is that the principle of superposition of waves states that when a number of waves travel through a medium simultaneously, the resultant displacement of any particle of the medium at a given instant of time is equal to the algebraic sum of the displacements due to individual waves. Okay, so what does this mean? Look here, suppose there is a string, there is a string, there is a string, and two waves are, or two disturbances are produced at the two ends. One is this one, you can see that because of this disturbance, the element of the string over here is vibrating or oscillating or gets displaced in the upward direction. I'm just taking this as y1, and this particular disturbance or the wave is propagating in the right hand direction. Okay, if I say this is positive x, so it is propagating in the positive x direction. Okay, and at the other end, another wave of similar amplitude, let us say the displacement, this particular disturbance is producing on this particular element of the string is y2. Okay, now this wave is propagating or progressing in the negative x direction. Okay, in the negative x direction, and see, they will progress towards each other. So according to principle of superposition, when they overlap, as they are progressing, as you see, they are progressing, the distance between them are decreasing, them is decreasing, and eventually they will overlap at certain instant of time. Suppose at any instant of time, both of them overlap. So look, this element, this particular element of the string where both the waves overlap. So according to my superposition principle, the displacement of this particular element of the string, according to the principle of superposition, will be y is equal to algebraic sum of the displacement produced by each or individual wave. Okay, this one. This is the principle of superposition. According to principle of superposition of wave, I can write the resultant displacement at this particular position or the element at certain instant. So overlap means both the waves are passing through the same particle or same set of particles of the string simultaneously, and upon superposition, what will be the resultant displacement of this particular particles on the string? So that will be given by superposition principle, and that is algebraic sum of the displacement produced by each. Suppose this is y1, this is y2, so I have written over here. And exactly you can see if you closely look these figures, so both of them actually have the same displacement. Amplitude of this displacement, suppose this is positive a, and this has amplitude of the displacement negative a. So if we add both of them, you should be getting zero displacement according to the figure. Zero displacement. That's why you look here, this black sign means the element is not displacing or not oscillating, rather it is at this position itself. Whereas you look, when the element of the string over here is displaced in the upward direction, so there is nothing drawn here, it is empty. Here also it is empty, but here you look, the black line is there. That means the string is not at all vibrating or oscillating. Because why? The displacement, resultant displacement becomes zero. Okay, resultant displacement becomes zero because the displacements are in the opposite direction. Actually these two waves which are having the same amplitude and same angular frequency and traveling with same speed in the opposite direction, exactly opposite direction, and they have exactly opposite amplitudes, so these are actually called the waves with 180-degree phase or pi radian phase or out of phase. So this will be discussed in the next slide. So this is the mathematical expression whatever I have said in the principle, that if there are number of waves which produce displacement like y1, y2, y3, and suppose there are n number of waves passing simultaneously through a particle, so what will be the displacement of the particle? That I can write by taking the sum of all of them, so y1 plus y2 plus y3 etc. And these displacements are actually position function of the position and time. And see if these are traveling the positive x direction, so the waves can be, or sorry, yes, the waves can be expressed in terms of this f of function of this as vt minus x if it is traveling in the positive x direction, and if the wave is traveling in the negative x direction, then here should be positive sign. Okay, in the negative x direction. So we have considered, suppose the waves are traveling the positive x direction, then we can write the resultant displacement of the particle through which all the waves passing at particular instant of time simultaneously. Then the displacement of that particle will be f1 vt minus x, f2 vt minus x, plus dot dot fn minus x. So this you can go up to nth term, or and this big summation can be, or addition can be written by very short notation, writing like this. So this is actually sigma sign. It is called summation. Here I in the down I, j, k, whatever indices you can use. At the same time, you have to use here, okay, bt minus x. So this I will change according to the limit you give. Suppose it's the limit or the I starts from 1, so and it goes up to n. Then this means you have to, let me write it here. This is called actually summation. This you should learn here, summation sign. So summation sign is like this, and there should be limit, suppose 1 to n f of vt minus x. So this, if we elaborately write, see each time I'll just increase. So the first term will be f1 vt minus x. Then I have to take summation. Then I will increase to 1. So like that it will go 1 to n. Okay, vt minus x. So like that it will go up to nth term. So this is the significance of this summation. So instead of writing this elaborately, we can write in a short notation. This is called summation sign. Okay. So this is about principle of superposition. Now what we'll do, we'll just go for a mathematical derivation. And as I said, when the waves are out of phase by pi radian or 180-degree out of phase, then the displacement the waves produce at a particular particle will be 0. So that we can show you theoretically or mathematically. Okay, let me clean this. Let us suppose there are two waves. Okay, let us suppose there are two waves. Waves having same angular frequency, same angular frequency, and same wave number, same propagation vector, or same wave number, and traveling in the same direction, So how would we but they are phi phi phase. Okay, they are actually, let us say they are out of phase by a constant phase angle, phi. Okay, so how to represent? So there are two waves, I said. Suppose one wave is y1, and obviously you can write as a function of x and t. Let us take sine kx minus omega t, one wave. The second wave, a sine omega t, both are function of sine. So you can see they are out of phase by constant phase angle phi. Otherwise, k are same. That is the propagation constant, or you can say the wave numbers, and this angular frequency omega are same for both, and both are actually traveling in the same direction, as the sign of these two are same, and also this omega t are same. Okay. Now the amplitude are also same. Both are having same amplitude a. Okay, this is the thing I have supposed. Now see, I just want to see when they are simultaneously passing through a particular particle in a medium, then what will be the resultant displacement produced by both of them? So what is the resultant displacement? y1 plus y2. So when they pass simultaneously, that is called overlap. Okay, that is called overlapping. After overlap, after superposition or superposition, sorry, SUP, upon superposition, superposition means overlap also. Upon superposition, displacement, resultant displacement will be y is equal to y1 plus y2. Okay, let me, so I have written the things, facts. I hope you remember the facts. I'll just go with the mathematical part. So I have written y1 x of t is equal to a sine kx minus omega t, and another one. See, this can be written even in either way also, omega t minus kx. In that way also you can write. I have taken another wave, phi out of phi phase angle out of phase. Okay, the resultant will be y1 xt plus y2 xt. That means a sine of kx minus omega t plus this. Now you have to actually use one trigonometric identity. So what is that identity? Sine of alpha plus sine of beta, you can write in terms of product. This is in terms of addition, you can write in terms of multiplication. So how to do that? 2 sine of alpha plus beta by 2. This is actually a trigonometric identity which we are going to use for this addition. Okay, and cosine of alpha minus beta divided by 2. So this identity we are going to use for this particular summation or addition. So resultant displacement, if we use this particular trigonometric identity, see a will be coming out anyway. So this is, suppose this is alpha and this whole thing is beta. So first will be alpha plus beta by 2. So if I write alpha plus beta by 2, what is going to happen? Alpha plus beta by 2. So this is alpha, this is beta. So kx, all of them will be actually twice, and this will be only 1. So look, this is sine kx minus omega t plus phi by 2. Just you can look at once again. So this is alpha and this is beta. So kx, So twice kx and minus 2 omega t. If I divide with 2, so this will give you kx minus omega t, and this is pi by 2 because there is no pi over here. Okay, this is one term. And cosine terms, you have to just subtract. So if you subtract this kx and omega t, these two will actually cancel each other, and eventually you will get, so alpha minus beta. So cos of minus phi means phi itself, so we can write phi by 2. So what we get actually from here, obviously there will be 2, so 2a cos of phi by 2 into sine of kx omega t plus phi by 2. So you can see this wave, this is also a propagating wave which is propagating in the same direction. See, in this case, in this figure, when I was, okay, let me clean. See, upon overlap, there is no change in the propagation of the wave, isn't it? There is no propagation, no change in the propagation of the wave. See, this individual wave, it is actually propagating. See, after overlap, also they just keep on propagating. So there is no change. So there will be no change, no hindrance, even after overlap. There will be no hindrance to the propagation of individual wave. Okay. Here, the propagating wave. So this overlap or the superposition of the wave is also a propagating wave, which is same propagating constant or propagating vector traveling in the same direction with the same frequency. Only one change is there. There are actually two changes. So first change is in the amplitude. The amplitude has become, instead of this a, amplitude a, earlier it was a for each of them. Now it has become 2a. The whole thing we can take as amplitude because there is no time factor over here. So this is not a function of time. So it is not propagating. This is a constant term. So 2a, so it is the amplitude 2a cos of phi by 2. Look, this is actually the new amplitude now for the resultant wave or resultant displacement. And see here, the overlap, upon overlapping, the resultant wave is actually is out of phase by pi by 2, not phi. The phase actually has been altered by pi by 2. Earlier the phase, the two waves, individual waves were out of phase by a constant phase angle phi, but now this resultant wave is actually out of phase by phi by 2 from each of them. Okay, from each of them. Okay, so this is the change we have got. So upon overlap, what is the amplitude? See, now I'll write what is the resultant. We'll write here. Resultant is 2a cos of phi by 2. So this is the amplitude term and this is the propagation term or the time varying function k x minus omega t plus phi by 2. I have discussed what are the changes over here. So in the phase angle and in the amplitude. Now look, whether the displacement will be maximum like this or it will be 0. How do you understand? From this amplitude, if the amplitude is becoming maximum, then you will get the maximum displacement for the particle after overlap of the waves. If they are overlapping out of phase, then it will be 0. Let us see that. So when the phi, the phase angle is 0, then what is the amplitude? Amplitude is 2a cos of 0. That means it is 2, twice of the amplitude. See, if I have two waves propagating in the same direction, and both of them have the same amplitude, say, Then upon overlapping, so they will actually produce amplitude twice of each of them. If it is A and this is also A, this amplitude will be 2A. Okay, so this is the case when the phase difference is 0. Okay, when the phi phase angle is 0, that means when they overlap in phase, see these are in phase, they are in phase, then you get upon overlap you'll get like this. Okay, but if suppose the phase angle is pi, or they are out of phase by 180°, that means one is vibrating in this way, another is vibrating in this way. Upon overlapping they will give you nothing, 0, because see cos of, see here A will be 2A cos of phi is pi, means pi by 2, so pi by 2 will give you 0. Okay, okay, so if this is pi, so it will be pi by 2, it will give you 0. If the amplitude is 0, that means the string, if suppose this is the string is not vibrating upon overlapping, so after overlap again they will vibrate, but this will progress this way and this will progress this way. Okay, this is the way. Okay, so this is about superposition of waves. Now we'll go to, so when the resultant will be 0, I'll write it over here. If the two waves are completely out of phase, if the two waves here, when we have taken two waves, if the two waves which are overlapping, two waves are out of phase, are completely out of phase, that means 180° phase difference is there, completely out of phase, then the resultant displacement of the particle reduces to 0. Okay, reduces to 0. So this is what about the superposition of waves. Now we'll learn about, okay, so this is the thing shown over here. See, if there are two waves, when the phase difference is 0, then the amplitude is actually become maximum. Suppose these are the two waves, sorry, this is the resultant, this is the resultant of the resultant wave, or amplitude of the displacement of the resultant wave when the phase difference is 0, and when the phase difference is pi radian, then there is no displacement, so you will get 0 displacement. Okay, now we'll go to the reflection of the waves. See, we have seen so far, when wave is propagating in an unbounded medium, then we have seen what happens to that. But if the wave propagate in a medium where it encounters a rigid boundary, then what happens to the wave? So this is our problem now. So this is the situation. So we have seen when wave travels in an unbounded medium so far. Now if a wave propagates in a medium where it may encounter a rigid boundary, then reaching or encountering to the boundary, what would happen? So what is the common sense? Common sense says that there will be a reflection. Okay, of the wave. That means wave will get reflected from that boundary, isn't it? So this is the common sense. We have seen, I hope you have read in your 10th class, the reflection of light. Light is also a wave, but we have read in terms of ray optics. But anyway, so when you see there is a reflector, suppose a plane mirror, what happens? This is the perpendicular, so it actually gets reflected. Okay, we'll see in the 12th standard wave theory of light, so it gets reflected. Okay, not only that, if the medium, the reflecting surface or the rigid wall, this rigid support or the boundary is interface of two medium like water and air. If this is the interface, then what wave does generally, there will be refraction. Okay, there will be refraction of the waves. That's what we have seen in terms of in case of light, also in terms of ray. But the same thing we'll learn in terms of wave in 12th standard. But anyway, these are the things when we see in case of light. Since light is an electromagnetic wave, things will be little different than the other wave, which are elastic waves. But the thing is that there can be rigid boundary, two types of boundary. There could be two types of boundary. One can be a completely rigid boundary. Another can be somewhat, okay, so elastic boundary. Okay, so there could be two things. One a very fixed or rigid boundary, another can be a boundary which is not that rigid. Okay, not that rigid or flexible we can say, rigid and flexible boundary. Okay, so we'll see in two cases what happens when the boundary is rigid, completely rigid, and when the boundary is not that rigid. The boundary is an open boundary, you can say, or the boundary we can say uh, flexible boundary or open boundary. Okay, so look, I have two figures over here, A and B, and there are different situations shown over here. See, this is a rigid wall. Suppose this is a rigid wall. Sorry, rigid wall. I have a string. You can see this is a string. So one side is fastened tightly with the rigid wall. Okay, with the rigid wall. And then there is a disturbance produced in the string, and suppose the disturbance is traveling towards the wall, and it comes and strike at this fixed or the rigid support over here. Anyway, this support is not going to move or get displaced with the wave. Okay, with this displacement, the rigid support is not going to displace. Okay, if this is the case, see what happens when the waves comes like this all the way, and then just go and hit over here. So rigid wall, what will this rigid wall do? Rigid wall actually will give, according to Newton's third law. So since the wave is giving an action here, it will produce a reaction of equal magnitude, but the reaction will be in the opposite direction. Therefore, there will be a wave produced in the opposite direction. You can see this is the wave when it is approaching the rigid wall, and after getting reflection, this is actually called reflection. After getting reflection, it is actually according to Newton's third law, action and reaction. So this is the action, and the rigid support or rigid wall will actually give a reaction. That reaction wave will be exactly in opposite phase. So these waves are actually 180-degree out of phase with each other. 180-degree out of phase with each other. So what we can say, when a traveling wave is reflected from a rigid or closed boundary, rigid or closed boundary, it is reflected back with a phase reversal, phase reversal means, here see, this wave and this wave are actually completely out of phase. That means 180-degree phase difference is there now with this incoming wave and reflected wave. Phase reversal or phase difference pi radians. I'll just repeat what I said. When the string is actually fastened rigidly to a fixed wall or fixed support, then this point where the string is supported is not moving with the wave. That's why when this wave strikes the wall, it will produce a reaction according to Newton's third law. So that will produce a wave which will be reflected, which will be actually having the same amplitude, but it will be traveling in the opposite direction, along the string. Okay, opposite direction to the incoming wave. Incoming wave was coming like this. Now the reflected wave is going like this. So the main point over here is that the fixed point will not move. So this will have zero displacement. So zero displacement for the fixed point, rigid point. So if see, we'll see in the later point when we have a organ pipe closed, one side closed, so we'll see there will be no displacement over here. So there will be node created over here. Okay, at the whereas at the open end there will be antinode. So antinode and node we'll be discussing tomorrow. Now we'll discuss about another case when the support is not that rigid. When the support, you look this, there is a ring. This is a rod, and this is a ring with which the string is fastened, and this ring can move up and down frictionlessly, okay, without any friction over the ring. Now when the incoming wave comes over here, so this point, this ring will also move with the wave, so because of that, the reflected wave, actually both the wave will be like this. Okay, both the waves will be in the same direction. They will actually add to each other. Okay, so when the pulse from the pulse actually hits this ring, the ring also oscillates, and this will create a reflected wave which will travel in the same direction. In fact it will be in the same phase. The reflected wave will be in the same phase. Okay, as the ring moves up, it stretches the string and produces a reflected crest which travels back towards. Actually, it will move in the opposite direction, but it will also create a crest over here, not a trough. Okay, so it will also create a crest over here. That means like that it will be created at the ring. So both are actually crest, but this wave, since it is a reflected wave, it will actually travel in the opposite direction. And in this case, there is no phase reversal. That's what we want to note. No phase reversal will happen. No phase reversal. No phase reversal. They are actually traveling in the opposite direction, but no phase reversal. You can see that. So this is the incoming wave in the same direction, oscillating in the same direction, and which is reflected also. The particles in the string oscillate in the same direction. So that's why it is no, there will be no phase reversal at the open end. At the open end, this is the rigid support. This is actually flexible support or open end, I can say. So what we can say from here, we can say that when a traveling wave, when a traveling wave is reflected from a free or open boundary, it suffers no phase change. It suffers no phase change. No phase change. Okay, so that's why, as I said, when you have open organ pipe, you will see there will be antinode produced. Okay, antinode produced. There will be displacement here also at this boundary. Okay, free boundary or open boundary. That's why you will see antinode produced at the two open end in case of open organ pipe. This we'll learn tomorrow about the standing waves and normal modes. We'll discuss tomorrow. Okay, so bye for today. Thanks for your patience.